What am I writing? Inter 23 P42. It's an electron in a metal rod. Moves randomly about a mean position. So this one is a scenario where we are looking at alternating current, okay, about a mean position. So without a current, without any current, if I zoom in and look at a metal rod, here's what we hypothesize the movement of the electrons will be. They will move or vibrate randomly. They don't really have a direction. They just move however they want. Okay. But once I connect this metal rod to an alternating voltage, so connect this to AC, yoink, the mean position can be considered to oscillate along the axis of the rod. Okay, so that means now the electrons will oscillate like this. This was the first time we saw this in an exam paper. Last time it was just my fever dream. Whenever I teach AC, I tell students, hey, do you know that AC is actually electron in simple harmonic motion? Because hari ini, we'll use the simulation to see this. We throw out some wires. And the AC voltage. It switch. The switch cannot be longer, which hurts me, but okay. Wire. Okay, let's put a light bulb now, just so that we got some bling. I am going to put a voltage charge here. So electrons doesn't look like it's moving, but they are actually vibrating around a fixed position. Okay. Should also the card. Okay, let's go. Because this is a low frequency AC, 0.5 hertz only. Okay. You can actually observe that the light will become brighter and dimmer, brighter and dimmer. But it's a bit trippy. Let me put this on here. It's a bit trippy because in real life, we don't see it because our AC is about 50 hertz, 50. Okay. But observe the electron. Let's look at one electron. Do you see that the electron is just oscillating in place? Electrons is in simple harmonic motion. It looks like, if you just look at it, it looks like the electron is moving clockwise and counterclockwise, but actually no, the electron just oscillate at this position. And you can see the AC tracing here and here. Okay. Right. So this is what is going on. You will see this is the vibration of the electron about the mean position. If you want to find the mean position from a fixed point on the axis of the rod, here is the mean or the equilibrium position. Okay, another way to detect the equilibrium position, if generally it's hard looking at this kind of graph for you, is to take the maximum value and the minimum value and then divide by 2, because here to here is 2a. And this is, I don't like this scale, 7.2. That means this is 3.6. Down here is 3.6. Okay, determine the amplitude of oscillation. Just did 1 mark only, so no need to show working. 3.6 times 10 to the power of negative 15. Okay, moving on. Of course, you can show some working now. You can. I mean, I'm a bit paranoid generally, so I will show working one. Okay. Determine the angular frequency omega. Omega is 2 pi over t. As usual, the first order of business is to determine the important constants where possible, whether it's from the context, from the scenario, from a graph, from a story. So I have the period. The period looks like 0. No, it's not. Is it? Yeah, 0.2 microsecond. My friend, if you already have painful experiences of losing marks because you did not look at the axis during the exam, I see axis or I circle one. I circle with pencil, and then I come back and erase if I have time. If I don't have time, it's fine. No need to erase. What is not fine is if I don't get the right answer because I forgot the prefix. Okay. Anyway, this would be 3.1 times 10 to the power of 7. Now, this is a proper AC, not some measly 5 hertz, okay? 1 mark. Use your answers to show that the maximum drift speed is this much. Well, maximum drift speed, A omega 3.6 times 10 to the power of negative 15, 3.1 times 10 to the power of 7, and I will get 1.1 times 10 to the power of negative 7. So you know the equation of A omega 1 mark, we'll substitute 1 mark. It's not all just 1 mark lah, so it's working, at least one line of working with substitution is 1 mark. Okay, moving on. The rod has a cross-sectional area of 4.3 cm square, contains a number density of conduction electrons this much, and all of the conduction electrons in the rod may be assumed to be oscillating in phase with and the same amplitude as the oscillation shown in figure 4.1. So all the electrons, they move exactly following this graph. Magic, okay? So basically we can assume all the electrons are identical, meaning they will have the same V naught. Use the information to calculate the magnitude of I naught for the maximum current in the rod. So I don't know whether you remember from your AS, but I is equal to NAV, NAV. So I forget now. Okay, if you forget, okay, I'm going to scroll up so you get the full effect. You see this equation is still in your formula page. So no. ANVQ. Okay, then you write ANVQ. Still got. So be familiar with your formula page, or don't forget TAS equations. All right, so if I want maximum current, the only thing that can be maximum is the speed. Everything else is constant. But so put everything is 8.5 times 10 to the power 28, 4.3 cm, 10 to the power negative 4 cm squared. V naught was 1.1 times 10 to the power of negative 7, a very slow electron. 1.6 times 10 to the power of negative 19. Booking calculator should give me 0.64. Okay. All right, part 2. Sketch how the IT graph will change. 2 marks. And use your answer in A2 and B1. A2 is this one, omega. B1 is this one. To determine an expression of I in terms of T, where I is in ampere and T is in second, so they want an equation, and determine the RMS current in the rod. Can I do the easy question first? IRMS is maximum current divided by √2. I mean, because I'm reading the question to preempt myself. 0.45. Okay, so now I got to figure out what the equation of the graph look like and basically how the graph look like. I am going to yoink the graph from the question. Give me a second. And while you wait, why don't you think about how the graph can potentially look like? Yes.
Hi.
What's up? Okay. So here are a few things that I know. I know that the period is 0.2. So I should see 2 cycles of AC. I know that the maximum current is 0.64, but I don't even need to because they already labeled I naught for me. Okay, very nice. So what else do I need? I need to figure out the shape of the graph. Do I just copy a negative sign shape? Do I flip the graph? What's going on? Well. Let's think about it. This one is the electron, correct? So if this is the electron and I want to find the speed of the electron, speed of the electron would be differentiating the displacement of the electron. So I am differentiating, I'm going to measure from the equilibrium position now, okay? Just to make my life a bit easier. So let's say this is x naught. So d dt, x naught sine omega t with the negative in front. So this means the speed of my electron will be negative x naught omega cos omega t. Now you might be thinking, I should now draw a negative cos graph. Nope, because this is the speed of the electron. Where is the convention current flow? Is it together with the electron or reverse with the electron? Reverse, right? Electron and current is reverse. Okay, GG. So hence current will be positive I naught cos omega t. The sign here is different because current and conventional current flow and electron flow, opposite direction. Yeah, this one will continue to haunt scientists for generations, but it's okay. We'll deal with it. All right. So we're going to draw positive cos. Positive cos starts from here. Here. When you draw a cos graph, do take the initiative to make sure that the important points, like the maximum points and the 0 points, where it cuts the axis, is accurate lah. And the curvature should also look reasonably accurate. Yeah, this is difficult one. Okay. Another way to tell the direction, if let's say you don't want to differentiate because differentiating is not part of your toolkit, is to consider the gradient. The gradient here is the steepest. So here, maximum negative gradient. And then because this is electron, so it's maximum positive I. Because it's electron. So electron opposite direction to current. Maximum positive I. And then at this point, I will be equal to 0 because there is no gradient. Then here, this point, which is 0.1, the reverse law, maximum positive gradient, maximum negative value. So I guess maybe, hang on, I'll just put this underneath. Ding, ding, ding. Oops. So for me, I personally prefer to just use calculus lah. That way my brain is happier, not so pain. But if calculus is not something that you have, then you need to consider the gradient. So you can see this gradient will give me this value because it's negative gradient, positive I. Gradient is equal to the speed of the electron, but speed of the electron opposite direction to I. So this is negative, this is positive I. Just like here is 0, so here is flat. Having a preference is a privilege, okay? If you only have one method, or there's only one method that is possible in solving the question, that will not be okay. So it's okay to know more than one. Negative current because positive steepest gradient. Okay, so you can actually map point by point one. And once you map for the first half cycle, you already know how the graph will look like already, positive to negative, then you just continue the story, right? So for this particular question, it's intentionally difficult one because we want to filter out, or rather the intention of the question is to filter out the better students. So in this case, check where the marks are again. The marks will be 2 cycles of sinusoidal curve. So 1 mark, I see 2 cycles. I don't care whether it's positive sign or negative sign or whatever, don't care. Okay. And then 1 mark is when you start with I is equal to positive I naught when t equal to 0 here. If you start here correctly and you are drawing sinusoidal curve, you will get 1 mark. Okay. If you start here correctly and you draw 2 cycles, you will get 2 marks. Most of the time, people will get the first mark lah. They may lose the second mark. Okay. So based on this, can we write the equation of the graph? I already have the general equation here already. Here. I is I naught cos omega t. Okay. Or I guess you can sketch the graph and look at the graph and see that it is cos. No? I is equal to I naught cos omega t. But I want I in terms of t. So anything that is not IT have to be substituted. So in this case, my I naught was 0.64 cos omega. Have we calculated omega? I think we have to calculate it. Omega is 2 pi over t. T is 0.2. So 2 pi over 0.2. Wait, I feel like we calculated this already. Yeah. 3.1 times 10 to the power 7. Okay. I said no need to calculate. 3.1 times 10 to the power of 7 t. So this is your equation. 2 marks. 1 mark is if your equation is in the form of I is cos omega t. So if I see cos t I, get 1 mark. The second mark is when this answer is correct. Of your answer in A part 2. No, this is your answer in B part 1. This is your answer in A part 2. The so-called ECF lah. All right. So on my equation line, I will straight away write this one 0.64 cos 3.1 times 10 to the power of 7 t. 2 marks. Okay, we have already determined the root mean square. So the difficulty lies in deciding whether you should draw a sine graph or a cos graph. You can use gradient to help you, but if you are a little bit more capable, you can definitely use differentiation to help. Okay, I want to go and stare at the examiner report. Hang on. Most candidates realized they need a sinusoidal curve. Many candidates found it difficult to draw a curve with the correct curvature. Okay, so sometimes they draw a sine curve, sometimes they don't even curve it properly. Okay, so these two, generally only the stronger candidate realizes that this is a coarse graph. Okay. Basically, Cambridge is telling us, get good, get good. So in short, the way to know that it's a coarse graph is either differentiating or checking out the gradient. All right, that's it for the simple harmonic motion graph. We should